Jai Hind to all. My name is Manoj Kumar, Assistant Professor, Department of Computer Science and Engineering, Ajay Kumar Garg, Engineering College, Ghaziabad. Today in this lecture, we will learn about the deadlock concept in operating system. So this is the content that I will discuss, I will cover in this video lecture. First, resources in context of the process and the operating system. After that, definition of deadlock, what is deadlock, and what are the necessary conditions for deadlock, and the situation when deadlock can occur in the system. After this, we will see about the resource allocation graph. What is resource allocation graph, and how we represent a resource allocation graph. Okay. So first one is the resources. So when we talk about the resources in a computer system, then resources, there are two types of resources in a computer system. First is the physical resources, second one is the logical resources. And physical resources are those resources which is required by a process to complete its execution. These are the necessary requirement of a process to complete its execution in the system. These resources are like processor, memory, input output devices. Okay, and the resources, physical resources in a computer system are available in limited quantity. So the main objective of a computer system or operating system is to allocate the resources in efficient manner to different process or multiple process running in the system at particular instant of time. These are another example of the resources like printer, semaphore and locks. These are the logical resources. Second resources are the logical resources. Basically, logical resources are those resources which doesn't exist physically, but they may be used by the process to complete their task, like a file or a variable in a program. So file or variable in a program, these are the example of logical resources. So whenever a particular program have to take an input from the file, have to access from the file, or want to write something in a file, then that file must be accessible to that particular process. In that case, that file is known as a logical resource. Okay, so process need access to resources in a reasonable order. It means the allocation of the resources to different process must be in efficient manner, so that or you can say that must be in a synchronized manner, so that resources can be allocated to each and every process, and each and every process can complete its execution. Okay. In case of preemption and non-preemption, we can classify the resources in two types. First one is the preemptive resources. Preemptive resources are basically those resources which can taken away from a process with no ill effect. It means whenever we take the process resources from the process forcefully, then it doesn't affect the working. That may be the preemptive resources. It means suppose a process is running in the system and it is using a particular resource. At the same time, if the process, a new process of higher priority is submitted in the system, okay, so which is a urgent process. So in that case, we have to taken away the resource from the currently running process, and we will allocate it to the higher priority process. Okay, so in that case, we are going to preempt that particular resource used by the P1. Second one is the non-preemptive resources will cause the process to fail if it taken away. Some resources are the non-preemptive resources. If we taken away from a particular process, then the process will not complete at that particular time, or it will affect the execution of that particular process. So second one is the deadlock. What is the deadlock? So whenever we talk about the deadlock, then deadlock is a situation in a system whenever progress of all the process in the system is stopped. Okay, suppose there are two process. First one is the process P1, second one is the process P2. Okay, and there are two resource type A and resource type B. So in here, process P1 is allocating, it means resource A is allocated to process P1, and resource B, process P1 hold resource A and request for resource B. It means process P1 holding a resource A and waiting for resource B. In the same way, process P2 is holding the resource B and waiting for a resource A. It means process P1 is waiting for a resource or requesting for a resource which is held by process P2, and process P2 is waiting for a resource which is held by process P1. Okay, and both process P1 and P2 need both resources to complete their execution. It means process process 1 will complete whenever whenever both resource A and B are allocated to process process 1. In the same way, whenever both resource A and B will be allocated to process P2, then it will complete. But here the situation is that A is allocated to process P1 and it is waiting for B, and B is allocated to process P2 and it is waiting for A. It means process P1 is waiting for a resource held by the process P2, and process P2 is waiting for a resource held by the process P1. So in this situation, the neither process P1 will progress or neither process P2 will progress. It means this is a situation of deadlock when the progress of process P1 and P2 both process progress will be stopped. So in this this is a deadlock situation. Okay. So using resources, how we can use the resource in a computer system. So whenever use of resources in computer system generally completed in 3 phases. First phase is the request the resource. Whenever a particular process need a resource, then it submit a request to the operating system. Now operating system will check the availability of that particular resource. If the resource is available at the time of request, then operating system will simply allocate the resource to the process. Otherwise, process have to wait until the resource become available. Okay. So first step phase is the requesting a resource. Whenever a process need a resource, then it will submit a request for that particular resource. Second one is the use of resource. If the resource is free and operating system allocate the resource to the process, then process will simply use that particular resource and it will complete its task. And after completing its task, third phase is the release the resources. Process will release the resource so that that resource can be used by newly arrived process. Okay. So we cannot use the resource if request is denied. Requesting process has option block and wait for a resource, continue without it may be able to use alternate resource, process fails with error code, or some of these may be able to prevent the deadlock. Next, again, this is the formal definition of a particular deadlock problem. So a set of process is deadlocked if each process in the set is waiting for an event that only another process in the set can cause. It means like here I explain, suppose there are 2 processes P1 and P2 and 2 resources. First resource is R1 and suppose it has a single instance. Second resource is R2 and it also has a single instance. This R1 is allocated to P1 and P1 is waiting for R2. R2 is allocated to P2 and P2 is waiting for R1. So here in this case, there is a set of process of 2 process P1, P2. Okay. And set of resources, 2 resource type is R1 and R2. So here in this set of process P1 is holding R2. Both process P1 and P2 required R1 and R2 to complete their execution, but P1 is waiting for R2 and P2 is waiting for R1. So this is a situation of deadlock. Okay. Neither P1 can progress and neither P2 can progress. So this situation is known as the deadlock. Next one is the necessary condition for the deadlock. What is the necessary conditions? These are also known as the characteristics of a deadlock. To justify that deadlock occur in the system, all these conditions must be satisfied. If any one of the condition doesn't satisfy, then there will be no deadlock in the system. Okay. At the same time, all these 4 conditions must be satisfied to say that there is deadlock in a system. First condition is the mutual exclusion. It means each resource is assigned to at most one process. It means resource must be utilized in mutually exclusive manner. More than one process cannot use the resource at the same time. Like for example, if R1 is assigned, one instance of R1 is assigned to process P1, then at the same time process P2 cannot be used R1. Process P2 will wait until process P1 will release R1. In the same way, one instance of R2 is assigned to P2, then at the same time process P1 cannot use the R2. Process P1 will wait until instance of R2 will be released by process P2. It means the resource instance utilization or resource utilization must be satisfy the mutual exclusion conditions. Resource must be shared in mutually exclusive manner. Third condition is the hold and wait. Hold and wait condition simply state that a process holding resources can request more than one resource. Like here in this example, process P1 is holding R1, okay, and waiting for R2. In the same way, process P2 is holding R2 and waiting for R1. So second condition is hold and wait for process P1 and also hold and wait for process P2. Suppose if there is this age doesn't exist, then wait condition does not satisfy, then there will be no deadlock. It means to state that there is a deadlock situation in the system, hold and wait condition must also be satisfied. Third condition is the no preemption. No preemption condition state that previously granted resource cannot be forcefully taken away from the system. Suppose it means if we allocated a particular resource to a particular process, then resource must be released by the process after its completion. If we are taking the resource forcefully, it means we trying to prevent, we trying to break the deadlock by ourselves. Okay, so in that case situation, deadlock will not happen if we are taking the resource forcefully. So another third condition is the no preemption. It means once the resource has been allocated to a particular process, then that resource must be released by process after its completion. We cannot take the process for resource forcefully from the process. If we do so, then we are breaking the deadlock condition by ourselves. Third one is the circular wait condition. It means there must be a circular chain of two or more processes where each is waiting for a resource held by the next process or member of the system. Suppose there is a process set and there are n number of processes P1, P2, P3, ... Pn. Okay. Now process P1 is waiting for a resource which is held by process P2, and process P2 is waiting for a resource which is held by process P3 up to ... In the same way, process Pn-1 is waiting for a resource held by process Pn, and again Pn is waiting for a resource held by process P1. Okay, there is a set of process P1, P2, P3 and Pn. So here a member of chain is forming. In this case, process P1 is waiting for a resource which is held by its next process. It means P2. P2 is waiting for a resource which is held by its next process. It means P3. In the same way, P3 is waiting for a resource which is held by process P4, and so on. And in the last, process Pn is waiting for a resource which is held by process P1. So here this is a cycle is formed, and this condition is known as the circular waiting condition. Here a chain is formed of the process in the process set, and cycle is also formed. So this is known as the circular wait condition. So to say that there is a deadlock situation in the system, at first we have to check all these four conditions must be satisfied. Next one is the resource allocation graph. Actually, basically, what is resource allocation graph? Resource allocation graph basically represent the system state at particular instant of time. It is used to represent the system state. Now, what is system state? Basically, system state contains the information about like how many processes are there in the system. Second, how many resource type are there. Third, how many instances of each resource type exist in the system. Fourth, how many instances of each resource type is allocated at a particular instant of time to the process, and how many resource instances or how many instances of a particular resource types are freely available, so that can be allocated to the newly arrived process. So resource allocation graph is a pictorial representation of the system state at particular instant of time, and that system state basically provide the information about the number of processes in the system, number of resource type in the system, number of instances of each resource type, or you can say that total number of instances of each resource type, and after that how many instances of each resource type is allocated to different process, and how many instances of each resource types are freely available. Okay, so generally in resource allocation graph, process are represented in form of circle, and resource instance are resource represent in form of a square, Generally we write the process inside the circle, and we write the either inside or resource or either outside the circle, and inside we represent the instances. Like here R1, and if it has 2 instances, then we will simply mention 2 dot here. Okay, so this is the resource allocation graph. If we talk about this particular graph, then it is representing that process A is using resource R. Here it means this age is known as the assignment age. In resource allocation graph, there are 2 type of age. Like suppose this is a resource allocation graph. So these are the resources, T and U are the resources, and C and D are the process. Okay, so this is known as the assignment age or allocation age. It means resource type T is assigned to process C, and this age is known as the requesting age or waiting age. Okay, it means process C is requesting for resource type U. In the same way, resource type U is allocated to process D, and process D is waiting for resource type T. Okay, so in resource allocation graph, there are 2 type of node. First node is used to represent the process, and second type of node is used to represent the resources. And there are 2 type of ages, assignment age and waiting age. Assignment age is from resource to process, is directed from resource to process, and requesting age or waiting age is directed from process to resources. So this is the resource allocation graph, which represents the system state at a particular instant of time. This is another resource allocation graph. Here in this graph, there are 3 processes, P1, P2, P3, and there are 4 resources, R1, R2, R3, and R4. And R1 is single instance resource, R3 is single instance resource, R2 has 2 instances, and R4 has 3 instances. Okay, and resource R1 instance of R1 is assigned to process P1, resource instance R3 is assigned to process P3, and one instance of R2 is assigned to P1, one instance of R2, other instance of R2 is assigned to process P2. Simply, process P1 is waiting for instance of R1, process P2 is waiting for instance of R3, and process P3 is requesting or waiting for instance of R2. So this is a resource allocation graph. Now we have to find from this resource allocation graph whether there is a deadlock in the system or not. So if there are 2 things, if the resources are of single instance, each and every resource has single instance, and there exists a cycle. So to detect the deadlock in the system from the resource allocation graph, at first we check that whether there is a cycle in the system or not. Okay, so like here, this is a cycle is formed. So once the cycle is formed, after that we will check the second condition, whether each resource type is of single instance or multiple instance. So if there is a cycle and each resource type is of single instance, then this is the sufficient to say that deadlock exists in the system. But if there is a cycle and resource types are not single instance, they are multiple instance, then to say that there is deadlock or not, we have to further use the algorithm or concept. We have to check the multiple instances status of the different resources. Like here in this particular resource allocation graph, there is a cycle, then there may be a possibility of deadlock. Now we will check that R2 has 2 instances, but both instances of R2 is allocated. Okay, so this resource allocation graph represent a deadlock situation. Cycle is exists in the system. One cycle is, sorry, here is not a cycle, cycle is here. This is a cycle. This is not a cycle. इसमें डायरेक्शन आपकी रिवर्स होगी. So this is not a cycle. Cycle is forming here. So in this resource allocation graph, this is a closed region, bounded region. Cycle is formed in this particular region, and this R2 is R3 is single instance, and both of instance of R2 is allocated. So this is a cycle, and since no instance is available, so this is a deadlock situation. But this is another resource allocation graph. Here there are 2 resource type, R1 and R2. Both resource type has 2 instances. Okay, R1 has 2 instances, R2 has 2 instances, and 4 process P1, P2, P3, and P4. Okay, one instance of R1 is allocated to P1, or one instance of P2, and one instance of is allocated to process P4. Now we have to check that whether there is the deadlock in the system or not, for which system state this graph is representing. So we can say that here cycle is forming here, but cycle is not sufficient condition to say that there is deadlock. Now we have to check again here, like hold and wait condition. P1 is holding the resource of R2, but there is no requesting ACE from process P1. It means P4 is not waiting for any other resources. So what will happen here? P4 will simply use this particular resource and will make it free. Whenever this instance will free, it will be allocated to process P3. Now the cycle will break. So there will be no deadlock situation. So for this particular graph, there will be no deadlock in the system, because here hold and wait condition doesn't satisfy for process P4. So in this case, process P4 will simply use this resource instance of R2 and it will release. As soon as this resource instance of R2 is released by process P4, and it will allocate it to process P3. When it is allocated to process P3, then this cycle will break and again it will complete its execution. It will release to R1 and R2, and this R1 will be allocated to process P1. Process P2 will complete its execution, and again process P2 will also complete, because process P2 doesn't need any other resources. Okay, so cycle is formed, but there is no deadlock in the system. So what is the conclusion? Conclusion is that if there is one instance per resource type, then existence of cycle is sufficient to say that deadlock in the system. But if there are multiple instances of resource type, then the deadlock may be possible or not may be possible. Okay, this is not the sufficient condition. In that case, we have to further check the status of the multiple instances of the different resource type to state that whether there is deadlock in the system or not. Okay, so in this this is another example for forming the deadlock. 3 process A, B, C and 3 resource type R, S, T. First R is allocated to A, S is allocated to B, T is allocated to C. Now A is requesting for S, B is requesting for T and C is requesting for R. So as soon as C is requesting for R, a cycle is formed here in this graph. So this is a deadlock situation. Okay. So starvation is another concept we will discuss in the next lecture, but generally I will give the overview here. Deadlock is the indefinite waiting, but starvation is a long time waiting. It means in case of starvation situation, the progress of some process will happen and some process will wait for a long time. But in case of deadlock, progress of all process will be stopped. Okay, this is the main difference between the starvation and deadlock. Okay, thank you. So today in this lecture, we will learn about the introduction of deadlock, what is deadlock and how it occurs in the system, what are the necessary conditions of deadlock. We have also discussed about the resource allocation graph, what the resource allocation graph is, and how we make resource allocation graph for a particular system state, and how can we detect whether there is a deadlock in the system or not with the help of the resource allocation graph.